I want you to imagine a rather bizarre scenario for a second. Imagine you are managing a fast food restaurant
Okay.
and you need to fill a position for a fry cook. But instead of hiring, a teenager looking for a summer job, you go out and you recruit a world-renowned, PhD-holding, Oxford-educated Shakespearean scholar.
That sounds incredibly expensive.
Right. You pay them this massive scholar's salary, and their only responsibility is to stand in front of a vat of oil all day and just flip a basket of fries when a timer beeps.
A total waste of talent.
Exactly. It sounds completely absurd, a massive waste of potential and money. But what if I told you that is essentially what the brightest minds in robotics are doing right now with artificial intelligence?
It's true. It is a profound overallocation of computational resources. And it's happening inside the architecture of, well, almost every advanced robotic system being developed today.
Which is just wild to think about.
It really is. We are essentially forcing digital polymaths to do manual labor, and we are paying a massive computational tax for it.
Welcome to this deep dive. Today, we're getting into a highly revealing preprint paper. It's from researchers at the University of Maryland and Cisco, titled Drop Then Recovery: How Redundant Are Vision Language Action Models?
A great paper.
Yeah, and our mission for this deep dive is to explore whether the massive, multi-billion parameter language models sitting inside today's cutting-edge robots are genuinely necessary, or, if they are just wildly over-engineered.
Spoiler alert, they might be.
Right. We're going to look closely at how these researchers essentially performed open brain surgery on an AI to find out, and what happened when the patient woke up.
What's fascinating here is that this paper functions as a brilliant piece of diagnostic work. We are going to uncover a very surprising inefficiency in how we approach robotic embodiment.
And it's going to change how we see these machines, right?
Absolutely. The results are going to force us to fundamentally rethink what these machines actually understand about the physical world they operate in.
Okay, let's unpack this. We all know the standard playbook for modern robotics. If you follow the AI space at all, you are intimately familiar with vision language action, or VLA, models.
Right, the VLA architecture.
Yeah, you take a powerful vision encoder, you bolt on an action module to control the physical joints, and you bridge the two with a massive pre-trained language backbone.
Which is the core of it.
We are talking about state-of-the-art models explicitly mentioned in this research, like OpenVLA, OFT, Pi 0.5, and GigaBrain 0.
The architecture is practically the industry standard at this point. I mean, the idea is that the vision encoder acts as the optic nerve, right?
Okay, makes sense.
And then the language model acts as the reasoning engine to process human instructions. Finally, the action module translates that reasoning into actual physical torque and movement.
But it's that middle component, the language backbone, that brings me back to my Shakespearean scholar analogy. Building a VLA today seems incredibly top-heavy.
It really does.
Like, developers are taking these giant pre-trained language models that have ingested practically the entire internet and can, write poetry or code, and they're stuffing them into a robotic arm.
Just to do basic tasks.
Yeah, just so it can follow a prompt like, pick up the red cup. The immediate question is why? Why inherit these oversized language backbones in the first place, instead of building a streamlined, purpose-built brain for the robot?
Well, it comes down to the brutal economics of modern machine learning.
Money, of course.
Always. Training a massive vision language model from scratch costs tens of millions of dollars. And it requires massive dedicated clusters of GPUs running for months.
So they just skip that step.
Essentially, yes.
Yeah.
Roboticists, understandably, take a shortcut. They leverage the open source ecosystem. They grab a pre-trained model that already possesses deep, web-scale, visual, and linguistic grounding.
The logic being, if this AI already fundamentally understands the concept of a cup, the color red, and the geometry of a table from reading millions of web pages, you just need to bolt that final action head onto it.
Right. And teach it to move a robotic arm.
It saves you from having to teach a robot basic object permanence from absolute scratch.
That is the operating theory, yeah. But this raises an important question, and it's the central thesis of the UMD and Cisco paper.
Okay, what is it?
How much of that massive web-scale language brain is actually needed for simple, closed-loop robotic control? Are we dragging around billions of dormant parameters that the robot never actually utilizes on the warehouse floor?
Which is a really tough thing to measure. I mean, you can't just interrogate the neural network and ask which layers it's using today.
No, you definitely can't.
But my initial thought when reading the premise was, if we suspect these VLA models are bloated, Why not just use standard compression?
Ah, right.
The industry has spent years perfecting quantization, or unstructured pruning, where you simply trim down the weights of the network to shrink the file size. So why did these researchers feel the need to invent an entirely new protocol called drop-then recovery?
It's because applying standard language model pruning to a physical robot completely ignores the mechanics of closed-loop control.
Wait, how so?
Well, if you use traditional unstructured pruning on a standard chatbot, just stripping away a percentage of the neural connections, the worst that happens is it might occasionally output a slightly ungrammatical sentence.
Or hallucinate a minor fact, right?
Exactly. The user reads it, maybe frowns, and moves on. The error is isolated, it doesn't break the system.
But a robot is operating in continuous time.
No.
It is constantly taking in new frames from its camera, calculating the next fraction of a second, and moving its joints.
Building on that, those tiny errors compound exponentially.
Oh, wow.
In continuous control, a slight miscalculation due to pruned weights doesn't just happen once. It causes the robotic arm to shift its trajectory by, say, 1 millimeter on frame 1.
Which doesn't sound like a lot.
But by frame 2, the camera is viewing the scene from the wrong angle, causing a 2 millimeter error. By frame 10, you have massive covariate shift, and the arm has completely missed the target or crashed into the table.
So the entire task fails just from a tiny initial math error.
The entire task fails.
I see the problem. You can't just shave the model down and hope for the best. You need a structural change, not just a surface-level trim.
Which is why they developed drop-then recovery, or DTR. Instead of just thinning out the weights, the researchers physically removed entire structural units.
Like completely took them out.
Completely. They excised whole transformer blocks for the language backbone. They essentially rewired the model so the data simply skips over those missing layers entirely.
Wow.
This creates a genuinely smaller, faster, dense model. But the critical step is the recovery phase.
Because if you just rip out half a brain, the robot is going to be paralyzed.
Precisely the point of the recovery phase.
Yeah.
They take this newly lobotomized model and fine-tune it on this specific robotic task. They give it a chance to relearn.
Oh, I see.
If the model can recover its original baseline performance after losing those blocks, it definitively proves that the removed architecture was completely redundant for that specific physical task.
That makes perfect sense structurally, but it immediately introduces a massive surgical problem.
How so?
Well, if I am performing this kind of radical architecture surgery, I need an incredibly precise scalpel. I can't just blindly delete blocks of code and pray the robot still knows how to open its gripper. How did they know which blocks to drop?
That brings us to their primary diagnostic tool, a novel metric they developed called GateProbe.
GateProbe. Okay.
Historically, if researchers wanted to drop a layer, they relied on static metrics. They might use something called cosine similarity.
Right, I've heard of that.
They would look at the tensor data going into a transformer block and the data coming out. If the input and output looked highly similar mathematically, they assumed the block wasn't doing much transformative work.
And they would just cut it.
Exactly.
But that feels like looking at a single frame of a movie and trying to guess the ending. Just because a block doesn't radically change the data in that exact moment doesn't mean that slight tweak isn't vital for a physical movement happening, 10 steps down the line.
That is the exact limitation of cosine similarity. It doesn't look at the whole picture. GateProbe solves this by operating directly in activation space, specifically targeting the downstream robotic action.
Okay, so it looks at the end result.
Yes. It introduces a virtual gate on the residual branch of each transformer block.
Let's get into the mechanics of that. How does a virtual gate actually function mathematically during the testing phase?
Think of it as a scalar multiplier, a digital dimmer switch initialized at a value of 1, meaning the block is fully active.
Right.
During the forward pass of the neural network, this gate scales the output of that specific block. GateProbe then uses backpropagation.
Okay.
It tracks the error signals backward from the final physical action of the robot, say, the failure to grip a cup, and calculates the gradient of the task loss with respect to that specific virtual gate.
So instead of just asking, is this block mathematically active?
Yeah.
It's asking, if I start turning this specific dimmer switch down towards 0, does the robot's error rate spike?
Yes, and that is a crucial distinction. GateProbe ranks the blocks based on absolute sensitivity. It calculates how much the final robotic action fundamentally relies on that block's contribution.
That's brilliant.
It is a highly efficient, one-shot metric that perfectly targets which layers have the highest potential for recovery without needing to retrain the model dozens of times just to test different configurations.
Armed with this incredibly precise surgical tool and the drop-then-recovery methodology, we finally get to the actual operations. What happens when they make the incisions? I
Wow.
mean, I imagine if you start amputating parts of the vision encoder or the action module, things go bad very quickly. You can't ask a robot to sort objects if you've severed its optic nerve.
Your intuition is entirely correct.
Okay.
When they targeted the vision action pathways, the result was total systemic collapse.
Not surprising.
Those components are incredibly sensitive. For instance, on the Pi 0.5 model, when they attempted extreme compression on the action module, dropping it down to just 2 remaining blocks, the success rate plummeted to a dismal 26.2%.
Oh, wow. It basically just forgot how to move.
Exactly. The robot lost its core motor functions entirely.
But the real target of the paper is the language backbone, the Shakespearean scholar. What happened when they started removing the language reasoning blocks?
They uncovered a staggering architectural asymmetry. The language backbone is highly, almost shockingly redundant.
Really?
Yeah. The researchers tested this on the widely used Libero simulation benchmark. They took the OpenVLA OFT model, and they removed exactly half of the large language model blocks.
Wait, they excised 50% of the language processing center? That has to be a massive reduction in the overall size of the model?
It equated to a 44.5% reduction in total parameters. And after the recovery fine-tuning phase, the model didn't just match its previous baseline.
Don't tell me it got better.
The performance actually improved. The success rate went from 95.0% on the massive full model up to 98.3% on the half-brained model.
Here's where it gets really interesting, because superficially, that feels like a paradox.
Yeah.
You take away nearly half of a machine's cognitive architecture, and it somehow gets better at its job. How is a smaller brain outperforming the larger one?
It has to do with optimization dynamics and the reality of compute budgets.
Oh.
They are fine-tuning this model on a specific benchmark with a fixed amount of computational power, right? The smaller, lighter model trains faster. It takes up significantly less memory in the GPU.
Oh, I see.
Consequently, under the exact same computational constraints, the dropped model can essentially iterate and optimize more efficiently on the specific task.
But that exposes a real blind spot in how we are utilizing these models. Like, how does it not miss all that complex language knowledge? How does it still know what it's doing?
Because of what the benchmark is actually asking the robot to do. If you look at current manipulation benchmarks like Libero, the instructions are incredibly short, rigid, and templated.
Like what?
The prompts are things like pick up the red cup or open the microwave. You absolutely do not need deep compositional reasoning to execute that. You don't need a model that understands syntax or context.
You just need basic semantic grounding. You need the neural pathway that maps the specific word red to red pixels in the camera feed and the word cup to the geometric shape of a cylinder on the table.
Exactly.
You don't need the AI to possess the cultural history of the color red. You just need it to know where the red object is right now.
And that requires very few parameters. To prove this, the researchers pushed the DTR protocol to its absolute extreme limit.
How far did they go?
They dropped almost the entire language backbone and kept just 2 language blocks active out of the entire massive model.
Just 2. Out of how many?
Out of dozens, just 2 blocks left.
And the result?
It still matched the original baseline. It maintained a 95.1% success rate on OpenVLA OFT.
That is a remarkable indictment of how we are building these systems. A multi-billion parameter model stripped down to 2 active language blocks, perfectly executing the task.
It's pretty eye-opening.
However, all of these numbers are from the Libero simulation, and, virtual environments are clean. There's no unexpected glare from a window, no motor friction, no unpredictable physics.
Right. The real world is messy.
Does this heavily compressed 2-block robot actually survive the physical world? Or does it completely fall apart when the lighting changes?
Transitioning from simulation to physical reality is the ultimate stress test, and the researchers tackled this head-on. They set up a real-world physical experiment using a Factory Gang 850 robotic arm.
Okay, a real physical arm.
Yes. They equipped it with a wrist-mounted camera and a third-person camera. But the most critical detail is the hardware they ran it on. An NVIDIA Jetson Thor.
Which is an edge computing device.
Exactly. This isn't a massive server farm in a data center. An edge device sits directly on the robot. It has strict, finite limitations on power, thermal output, and most importantly, memory.
Right, you can't just throw infinite cloud compute at it.
Exactly. In physical robotics, if your model is too large, the processing latency creates a deadly lag. If the robot takes an extra half-second to calculate its next joint movement, the physical object might have slipped, or the arm might overshoot its target.
So smaller, denser models aren't just a cost-saving measure, they are an operational necessity for real-time physical reaction speeds. What was the physical task they gave this arm?
They designed a highly complex warehouse parcel sorting task. The robot had to pick up soft body packages and sort them onto a conveyor belt or into a side container.
Oh, I imagine soft body packages are a nightmare for standard robotic grip calculations. A rigid box is mathematically predictable, right? But a deformable plastic shipping bag changes shape every single time you touch it.
The state space for a soft body object is virtually infinite compared to a rigid object. The visual boundaries are ambiguous. The center of mass shifts constantly.
So it's a huge challenge.
Huge. And to make it even harder, they hid solid medicine bottles inside these wrinkly, shifting plastic bags.
Oh, wow.
The robot only had a very limited graspable surface area where it could successfully anchor its gripper onto the solid object inside.
So it's essentially reaching into a bin of chaotic, shifting plastic to blindly find a cylinder. That is a massive step up from a simulated rigid cup. How did the compressed models fare against the baseline Pi 0.5 model in this physical chaos?
The pattern they observed in the simulation held up remarkably well. In their primary environment, the full, uncompressed model achieved a success rate of 63.3%.
Okay.
The Drop 9 model, where they amputated exactly half of the 18 language blocks, actually edged it out, hitting a 65.0% success rate.
So even in a complex, soft body physical task, half the brain is still entirely redundant. And because this is running on that constrained Jetson Thor Edge device, what did those dropped blocks actually buy them in terms of performance?
The efficiency gains were massive. The extreme compression model, the Drop 16, achieved a 1.64 times end-to-end task speedup.
That's a huge speed up.
It is. The physical actions were generated dramatically faster, drastically reducing latency. Even more critical for edge deployment, it required 42% less memory footprint.
Dropping your memory requirement by 42% without sacrificing core success rates is a massive win for hardware engineers.
Oh, absolutely.
You can instantly repurpose that freed up RAM to run higher resolution camera feeds, more complex safety constraints, or faster tactile feedback loops. But in engineering, there is rarely a completely free lunch. If you carve out half a neural network, you have to be losing something.
Right. If we connect this to the bigger picture, we have to interrogate why those massive language backbones exist in the first place, even if they seem redundant for basic sorting.
So what was the catch?
To find the hidden cost of this surgery, the researchers subjected the physical robot to out-of-distribution tests, or O-tests. They fundamentally altered the physical environment to introduce variables the robot had never trained on.
They started messing with the physics and the lighting to see if the compressed model could still generalize.
Precisely. They bathed the scene in a harsh pink light, then a green light.
Okay.
They introduced novel, unseen objects into the sorting bin to create visual clutter. They altered the physical orientation of the target container, and finally, they removed the sorting container entirely, leaving the deformable bags loose on the table.
And I'm guessing the highly compressed two-block model didn't handle that chaos very well.
Well, under mild perturbations, the compressed models held their own. But under severe environmental shifts, the underlying value of the full language backbone was exposed.
There it is.
Yeah. When they flooded the scene with harsh green light, the full, uncompressed model managed to maintain a 50% success rate. The extreme Drop 16 model plummeted to 35%.
A massive degradation in reliability.
And when they removed the physical container, entirely forcing the robot to understand the scene without its primary geometric anchor, the full model succeeded 60% of the time. The Drop 16 model fell to 40%.
That perfectly illustrates the trade-off. The massive language model wasn't just sitting there uselessly. It was quietly moonlighting as a robust physical adaptation engine.
That is an excellent way to frame it. Even though complex language parsing isn't required for the command pick up the bag, those billions of parameters contain vast webs of correlative data from their web-scale pre-training.
Right. All that internet knowledge.
Exactly. They hold dormant knowledge about how shadows warp, how colors shift under different light frequencies, and how materials deform.
Oh, that makes sense.
When the physical world goes out of distribution, the full model uses that deep, latent knowledge to stabilize the vision encoder's representations. When you drop those blocks, you strip away the robot's ability to intuitively generalize when the lights go out.
So what does this actually mean for the future of the devices entering our homes and workplaces? We've unpacked a lot of complex architecture today. We now know that the vision language action models powering cutting-edge robotics are carrying around massively oversized language brains.
That's the core finding, yes.
Using the GateProbe metric and the drop-then recovery protocol, researchers proved you can literally amputate up to half of those language blocks, retrain the model, and it will perform the exact same task faster while consuming 42% less memory on edge devices.
But the crucial takeaway is the hidden cost. We demonstrated that those supposedly redundant layers are secretly providing the physical robustness required to navigate chaotic, unpredictable environments.
It's a phenomenal piece of diagnostic engineering, but stepping back, it leaves me incredibly skeptical about the overall trajectory of AI robotics.
And that skepticism is entirely justified. What this research fundamentally exposes is a glaring flaw in how the entire AI industry benchmarks robotic intelligence.
The tests are just too easy.
We are pouring billions of dollars and megawatts of power into training colossal models, and then we are grading them on manipulation tasks so rudimentary that an actively lobotomized model with just 2 language blocks can ace the test.
Moving a red cup from point A to point B is no longer an adequate measure of intelligence.
It exerts zero pressure on deep linguistic grounding or complex compositional reasoning. If we are going to put massive language brains inside robots, we desperately require new, multi-step, complex benchmarks that force the robot to actually utilize that semantic power.
Which brings us to a final thought to ponder long after this deep dive ends. We've seen that simple, repetitive warehouse tasks demand very little cognitive architecture, while chaotic, unpredictable environments require the massive generalized knowledge of a full language backbone.
Right.
So perhaps the future of physical AI isn't about finding one perfect universal brain size.
They might not be.
If edge devices are choked by memory limits, but real-world chaos demands massive parameters, does this mean the future of robotics is a hybrid system? Will the robots in our homes and factories run on ultra-fast, lobotomized, 2-block brains for 99% of their daily tasks, only pausing to wirelessly download the reasoning power of that massive Shakespearean scholar from the cloud the exact moment they encounter a shadow they've never seen before?
It suggests a fascinating architectural split between reflex and reasoning.
Think about that the next time you see a tech demo of a robot gracefully navigating a perfectly lit, highly controlled laboratory. Thanks for joining us on this deep dive. We'll see you next time.